Hi, everyone. So let's do Pulleys chapter today in physics. Here we are talking about pulley systems, wherein as you come across a pulley, as you hear pulley, you would be, I hope, remembering the things of your village, wherein you see the wells and then you see a pulley, right? So it is nothing but a circular disc over which a rope is being inbuilt there so that you can just bring it on, you can just move on this load onto this and apply some effort here. This is called as effort. Here the effort is applied in the downward direction and the displacement of the load. This is my load. I use pulley to lift the loads, right? So pulleys are being used to lift the loads easily because from the well, if the water have to come up, then definitely we need to apply some effort here, and then the load will be coming up in the upward direction. So effort is put in the downward direction and load is bringing it up in the upward direction. So now as you see this, there is some tension in the string. There is some tension in the string, and this is called as T. Tension string. Tension is nothing but the force, tension force we say, right? So tension is nothing but the force that is experienced by this string here, by this string. And tension force is always in the upward direction here. As you see, if this is a point P is where I am applying the effort in the downward direction. Please try to understand that more clearly. Point P is where I am holding it, or I would say there is a person here, okay, holding this and drawing it downward. So thereby the effort is being in the downward direction, but the tension force is acting in the upward direction. Here also, if it is the same string, remember one thing, if it is the same string, the tension force remains the same in the both the strings, in the string 1 and string 2, both the strings here 1 and 2. So it is the same tension force which is applied, which is being caused in this string, right? The force which exists in this string is nothing but your tension force. And this is your single fixed pulley wherein axle is fixed to a rigid support. Here you will have a rigid support. Okay, then and an inextensible string is being put here. This is the string inextensible, that should not be having the elastic properties, and load is being lifted up by applying an effort in the downward direction. Then the tension in the string is considered to be the T in both the upward directions only. T upward direction, remember, T in upward direction. T stands for tension. T stands for tension, which is nothing but the force only, tension force it is. Okay, and this type of pulley is generally used in lifting small loads. Okay, not heavy loads and all, small loads. Now we have to talk about some important terms here as mechanical advantage, velocity ratio, and this one, efficiency ratio. So now mechanical advantage, if we neglect the mass of the string and the friction of the axle, so we do not consider the mass of string and friction in the axle, friction at the axle, both are neglected. Then your balanced position, like L is equal to your T, which means load is equal to the tension on my left side and effort is equal to the tension on my right side, right? So as you can see, this right side portion, right side, your effort is being put in the downward direction, tension in the upward direction. That is number 2 here. And in the first case, load is being pulled in the upward direction and tension also is shown in the upward direction, is your first case there. Now, this is also equal to T, that is also equal to T, implies, can I say L is equal to E, load is equal to effort. How much ever is the load, the same amount is the effort there. Now, if we have to talk about the mechanical advantage, this is mechanical advantage, which is load by effort. And load by effort is nothing but load is your tension, by effort is your tension, which is nothing but 1. So in case mechanical advantage is 1, it is 100% efficient machine, we would say. There is no gain in the mechanical advantage if the point of application of E moves a distance d. Here, I am applying, at some point P here, and it is moving a distance d. Then we talk about something called as velocity ratio. Okay, mechanical advantage talks about your how much is the load you're lifting and how much is the effort you are putting in there. So load by effort is the mechanical advantage, and VR stands for velocity ratio. And what is velocity ratio? Distance moved by the effort arm to the distance moved by the load arm, right? So as I'm moving in the effort in the downward direction, what is the distance moved by this, effort arm? And how much is the load arm moving upward? That distance is nothing but the same only because it is around the pulley. As you move downward, if you move 1 meter downward, it will come 1 meter upward, right? So therefore, distance of the effort by distance of the load, both same rahenge. So it is equal to 1, or I would say this is again, 100% velocity ratio. Now, what do you mean by efficiency? These are the three things we have to consider, very important things. Mechanical advantage is load by effort. Velocity ratio is distance of the effort by distance of the load, which is also equal to 1. And then your efficiency ratio. Efficiency is mechanical advantage by velocity ratio. We got here in this case of the one pulley case, fixed pulley case, mechanical advantage 1, velocity ratio 1, answer is 1, efficiency is 100%. If I have to talk about in percentages, I am converting this to 100%, right? 1 is 100%. So therefore, this is called as efficiency. And let me tell you, no machine in this universe is 100% efficient because there are some leakages of energies happening. So don't worry about that part. We will be doing it later also in these things coming up next. So now if I have something like this is your fixed pulley, right? This is your fixed pulley. Now the next type. So coming up with the next type is your movable pulley. So before going to the movable pulley, I want to clarify one thing again. Mechanical ratio is load by effort. Please write it down clearly. Mechanical ratio is load by effort. Velocity ratio is distance traveled by the effort arm by distance traveled by the load arm. Here in this case of fixed pulley case and one pulley case, it is going to be 1. So therefore, efficiency is always mechanical advantage by velocity ratio, which is anyway 1, which is 100%. Now let's move on to the movable pulley part. I hope I'm clear with this fixed pulley part. In case I'm going a little bit faster, please pause it, try to understand it, and then move further. Without understanding, please don't go further, bacha. Okay. Now, let's go with single movable pulley. The earlier case was single fixed pulley. Now it is single movable pulley. Okay, I have an axle which is fixed here. I have a hook over which I have put my pulley here. So here is my pulley like this. Oh, I'm bad at drawing this. Okay, one second. Here is my pulley, I would say. This is my pulley. The rope is, and looped like this over it. And then here my effort is in the upward direction. Effort is in the upward direction, right? So, and then this is my tension here. So this is my fixed pulley here. Right. Yeah. Now, here will be my axle wherein I'm fixing something here. This is again, because pulleys are used to lift something. Now, this is a hook wherein if I have to lift something, lifting a load, here will be my load fixed up. At this point, here will be my load fixed up. And I rise the effort to the upward direction. Then what happens? My load also pulls up to the upward direction, right? So therefore, that is how I can actually lift the load here. So single movable pulley suspended by passing an inextensible string again, negligible mass around the grooved rim, then load to be raised is suspended from its axle. One end of the string is tied to a hook, one end of the string is tied to a hook, and a rigid support is given there, and effort E is applied at its free end. And then as you see the tension in the string, yes, now coming up with the tension in the string, tension is always in the upward direction for the string. This is my tension force T. And as I told you earlier, if it is the same rope, we are not changing the rope, then tension remains the same. Here also one tension, there also one tension. Both are same. And here load is in the downward direction, as you can see here, right? So now we talk about mechanical advantage, velocity ratio, all these things here also. Okay, mechanical advantage, velocity ratio, and efficiency. Now, friction in the pulley and all, bearings and all we neglect, and weight of the pulley and the string also is being neglected, and the load is balanced by the tension in the two strings. Here, I would say load is balanced by tension plus tension. Both the strings here, the load is being balanced here, unlike in the previous case. Previous case, as you can see, I'm just showing the previous case also. See, previous case, as you see, tension is being pulled downward and then your load is being pulled upward, right? But here we have a different setup wherein this load is being pulled up by two tensions in both the strings, which means load is equal to 2T, right? Load is equal to 2T, and effort is nothing but effort is only 1T there, only one tension, but load is being pulled up by both the tensions here, both. So therefore, effort is equal to this. Now, can we say effort load from these two equations, load is equal to 2 times effort. Yes, can we say that? T, I can just substitute there. So load is equal to 2 times effort, or effort is equal to load by 2. Effort is equal to load by 2. So your effort is being reduced. When you use this kind of pulley, movable pulley, it is more easier now to pull up the, weights and all. So when the free end of the string is pulled up by the effort through a distance 2D, the load is raised up by only one distance, no? Right? So velocity ratio also, I would say distance in the effort arm by distance moved by the load arm, right? And distance moved by the effort arm here and here, it is two distance, whereas this distance moved by the load arm is only one distance, which is 2. So here velocity ratio I got as 2. And efficiency, if I have to talk about, MA by VR, mechanical advantage by velocity ratio. Mechanical advantage, we have it as, how much is that? 2 we have mechanical advantage there in the first case, right? So this is nothing but your mechanical advantage, no? Load by effort. See, load by effort is 2, which is nothing but your mechanical advantage. So 2 by velocity ratio, just now we got it as 2, which is 1. 1 matlab 100%. So here also efficiency is 100% what we got, right? So this is again a fixed pulley where we talk about, say a movable pulley where we are talking about, right? So let's go on further on this. Please write it down. Put a pause and write it in case you are not able to write it. All right. So next, moving up with the next part of it. Yes. So now let's talk about single fixed pulley and single movable pulley, the differences between them. Okay, single fixed and single movable. So what are the differences between them? It is fix it to a rigid support, fix it to rigid support. And this is not fixed here. And if I have to talk about second point, yeah, its ideal mechanical advantage is 1. Mechanical advantage here is 1, whereas in movable pulley, mechanical advantage is 2. Velocity ratio is 1. And in movable pulley, your velocity ratio is 2. We just now have discussed, right? And weight of pulley itself does not affect its advantage, whereas weight of the pulley also affects the mechanical advantage here. Weight of pulley also affects the mechanical advantage here in the single movable pulley, because you are also moving the pulley there. Here in the fixed pulley, you are not moving it. That's the reason weight does not matter for fixed pulley. And it is used to change the direction of effort from upward to downward, whereas it is used as force multiplier. Number, yeah, 5 here. Single movable pulley used as force multiplier, because you are actually moving twice two distance, whereas one distance is being lifted with the less load, less effort there, right? So load, what I say is load by 2 is equal to effort. That's what we got in single movable pulley, because which means that it is acting as a force multiplier there. You are actually using only half of the load. Some 100 newtons is the load to be lifted. Here in the single fixed pulley, you have to use 100 newton force to lift it. But here you can use only 50 newton loads effort, which will be only 50 newton load to pull a load of 100 newtons. So therefore, here it is used as a force multiplier. And number 6, load moves in a direction opposite to the effort. Load moves opposite to effort, but whereas here load moves along the effort, along the direction of the effort. So this is mainly the differences between single and movable, single fixed and movable. So now let us talk about a combination of pulleys as well. So for that, I would just have to draw a little small diagram here. I want you to also draw this along with me. Yeah. Now here there is a fixed portion. Okay, and this is fixed, and I am using a rope here. I'm using a rope, and here is my pulley. My rope is being pulled along like this. And then here another pulley I'm using, another pulley, and then this is also fixed here. And then my load like this. Now, so effort in the downward direction. So always try to draw those, arrow marks there. So effort in the downward direction, upward direction is my tension here. Here tension is upward direction. There also tension is the upward direction. So here if I say mechanical advantage, which is 3T, right? And which is 3, I would say mechanical advantage is 3, right? But what is mechanical advantage formula? Is nothing but load by effort. Now here load is T plus T plus T, whereas effort is only 1T there, right? So therefore 3T by T, which is your 3 there. Now, moving on to the next part of it. Yeah. So we do have some multiple pulleys also associated here. So what do I talk about them here? I'm going to show you there one second. Yes. Now here a hook, one pulley here, and then another hook, another hook. Like this, it goes on multiple times. Another pulley here, and then another hook here, and then like this. So it's like multiple pulleys, one after the other connected here, right? So wherein I can say what is my effort and all. Here is my effort. See, if I say this is my T1, all goes in the upward direction, but if this is T1, this part is my T1. Try to understand the things there, because this is the rope and that is different rope here. And here is my T2. then this will be my T2 here. The blue ones is my T2 here. And then the white one here, I would say this is my T3, here my T3, and this is my T3, and also this is my T3, right? So this is how, and this will be my load. This is my final thing, which is my load is being fixed up here, load is being pulled, right? So therefore, as you pull the effort, your load will be also moving upward direction, right? So effort will be pulling effort, you are applying the effort in the downward direction, whereas the load is being pulled in the upward direction. So this is your multiple pulley setup here, right? Now coming up to, yeah, I think now we are good to go with our numerical stage now. So let's go with the numericals on this to understand more on this concept. Now, coming up with your numericals of this chapter, let's do the numerical part here. So a woman draws water from a well using a fixed pulley. Mass of a bucket and water together is 6 kilograms given to you, bucket and water. Force applied by the woman is 70 newtons. Force applied is nothing but your effort. Force applied by the woman is effort, and calculate the mechanical advantage. Mechanical advantage is nothing but your load by effort. So remember that mechanical advantage is load by effort. Always be very careful using those things there. Oh, one second. One second, you know. So I have set up this thing now. Yeah. So now if I have to talk about the mechanical advantage for number of pulleys, n number of pulleys, if you have mechanical advantage is 2 power n, and velocity ratios is 2 power n. Efficiency is mechanical advantage by velocity ratio, which is 1 here, which is nothing but 100%. So now the question here is, a woman draws water from a well, wherein, as you can see here, the mass effort will be your 70 newtons. Load lifted by you is nothing but 60 newtons. So therefore, mechanical advantage is load by effort, which is 60 by 70, which is 0.857 is the mechanical advantage, not 100%. As I told, nothing will be 100% efficient there in the universe. So now next question, a fixed pulley is driven by a 100 kilogram mass at a rate of 8 meters in 4 seconds. Time is given to everything. It lifts a load of 7.5, 75 point this. Yeah, I can write it here. Yes. So now, as we have seen this, at a rate 100 kilogram mass is the mass falling at a rate of 8 meters in 4 seconds. So 8 meters in 4 seconds lifts a load of 75 kgf. Calculate the power. So power is nothing but your work upon time, right? And what is your effort there? Effort is nothing but mass into gravity, is nothing but force only. Mass into gravity. Mass is 100 kilograms into gravity is 10. So this is 1000 Newton you get. And the input power is nothing but your energy into time, right? So this will be your 2000 watts, as you can see here, 2000 watts. And load lifted by the pulley is 75 into 10. 70, this is load is 75 into 10, which is 750. And then you can talk about the mechanical advantage, which is L by E, load by effort, which is 750 by 1000. Mechanical advantage is load by effort, which is 750 by 1000, which is 0.75. So when the effort moves by a distance downwards, the load moves in the same distance in the upward direction. That is what we have known, right? It is for the pulley, the single. Next. So coming up with the next one there. Question number 3, single fixed pulley. I can just show you from here only. I think this is better, right? Everything is written also here. Question number 3 here. In case of a fixed pulley, effort, fixed and movable pulley. One second, one second. Oh, this is jumping here and there. Yeah, in case of a single fixed pulley, effort that is needed to lift a load is equal to the load itself. And a single fixed pulley, we have already seen that in the first lot only. Separately use it to lift 550 kg of the same height, compare the efforts and all. So if it is 50 kgf, effort arm, if it is a movable pulley, effort will be 50 by 2, right? So movable pulley mein, it is only half of the load is nothing but that effort we need. So only half of the load is the effort. So it is a force multiplier, we can say. Therefore, 25 kgf is enough for the effort. When we apply only 25 kgf, your 50 kgf load will be lifted up. And your ratio also will be 2:1 here. Then question number 4. In a block and tackle system, 3 pulleys are being attached. Their load of 75 raised with an effort of 25. See, you can see this load of 75 with an effort of 25. So which means N is equal to 3. Mechanical advantage is what? Is your load by effort, which is nothing but your 75 by 25. Load by effort is 75 by 25, which is 3. Mechanical advantage 3. The number of pulleys used is 3. If mechanical advantage is 2, number of pulleys used is 2 in the block and tackle system, right? If the mechanical advantage is n, the number of pulleys used is n here. So velocity ratio also is the same there. So efficiency will be 100% there. Right. Next, block and tackle system has 5 pulleys here. So 5 pulleys, N is equal to 5. So effort is equal to 1000 newtons is given to you. So load is equal to given to you as 4500, and mechanical advantage is nothing but load by effort. Load is 4500 by 1000, which is 4.5, and velocity ratio has got 5 because it is being used as 5 pulleys here. 5 pulley system is being used. So your efficiency is mechanical advantage by velocity ratio, as we have done with many questions. So which is nothing but your 4.5 by 5, which is your 0.9 or 90%. Next, moving up with the next question. Yeah, question number 6, as you can see, there is a block and tackle to lift the load, applying the force in the direction. Mark the diagram, the direction of the load and the effort. So as we have to now finish up the figure, upward you have 3 pulleys in the system and downward you have only 2 pulleys in the system. See, this is how we can show the effort. We have to lift the load in the downward thing. So to lift the load, start from here as I'm showing you my cursor. Start from here. Effort is pulling you down. Tension will be in the upward direction. You go on connecting them everywhere in this loop like this, and like this loop, right? So here effort will move 5 tensions, 1, 2, 3, 4, 5 tensions. Therefore, so all these 5 strings and the one string is your effort. So your load is 5T and the outward T here is your effort. So all this 1, 2, 3, 4, 5, all this 5T will be your load and T will be your effort. So you can actually rise by using this system. You can rise, this much of the load by using only 1/5 of the effort, 1/5 of the load. Effort is only 1/5 of the load that you are rising. If you have to rise 200 kilograms, it is only 1/5 of the 200 kilograms. Your effort will be very less. So it is again a force multiplier here. So mechanical advantage is 5 there. Yeah. Next, pulley system has a velocity ratio 3. VR is 3, it says. Mechanical advantage. Draw a diagram to show the point of application of load, effort, and tension, everything. So it is a system of 3. And it lifts a load of 150 newtons. 150 newtons, as you can see here, you can put 150 newton here. And effort of 60 newtons is being used. 150 to 60, it is 2.5. So, right? So it is 2.5, which is nothing but your 5 by 2, or you can just say that 2.5. So it is not ideal because mechanical advantage is less than 3. Mechanical advantage has to be 3 for 3 pulley system there. So it is less than 3. Therefore, it is not an ideal system. As we see, generally, there will be no ideal systems available. Next, draw a string around the pulleys. That you can draw, I guess. So effort will be pulled out, and then from the effort, you apply this chain rule like this: chain, 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 and go on like this. So how many tensions? Tension, 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 tension. All these four tensions is your load, and the effort wire as you're pulling down, that tension will be in the upward direction only. Effort is in the downward direction, tension in the upward direction. Tension will be your 1T, which will be your effort there, and mechanical advantages 4T by T, which is nothing but 4 there. And there is no friction. That is what have to be assumed. The weight of the pulley is also negligible. And velocity ratio of the system, you're using 4 pulleys there, N is equal to 4 there. So your efficiency is mechanical advantage by velocity ratio, which is 1, which is 100%. So yeah. Next question, question number 9. How many stands of tackle are supporting the load here? As you can see, 1, 2, 3, 4. 1, 2, 3, 4. 4T to 1T. So you can just see this also here. Yeah, mechanical advantage 1, 2, 3, 4. All these 4 tensions to 1 tension there, because the same wire being used there. So therefore, tension remains the same in the string. Whatever is the tension in the outward string is the same tension in the inward string as well. So mechanical advantage is load by effort, which is your 4 by 1, which is 4 there, right? So that is it. Then effort is equal to your mechanical advantage is load by effort. Mechanical advantage 4 you have, load you have 100, then effort is how much? That's what you get there. So you can use only 1/4 of the load, 1/4 of the load to pull up that, system there, to pull up that weight there. So that is a force multiplier. Next, you have block and tackle system has a velocity ratio 3, VR3, which means that it is having 3 pulleys, and system indicating the points of application of the directions of the load and effort. A man can exert a pull of 200 kgf. What is the maximum load that he can rise? So for efficiency, 60%, they say. See, efficiency is equal to 60%. 60% is nothing but your total of this. Na? So, or else we can directly go with this also. So 60% is equal to mechanical advantage by your velocity ratio. Here, velocity ratio is given to us, I guess, 3, right? I would write it here also. One second. Yeah. So here efficiency is mechanical advantage by velocity ratio. Velocity ratio is 3, I guess. Mechanical advantage, we don't know, 60 by 100, 60%, right? So which is 6 3s are 18 by 10 is your mechanical advantage there, right? These are 18 by 10. So that is how you can find out your mechanical advantage, and your load is N times E minus W. Okay, so which is nothing but your, or I would say this is nothing but 100%. 100% you take it as 1 minus this. Okay, and then you get this. Then velocity ratio is 3. So velocity ratio is nothing but distance of the effort arm by distance in the load arm, which is 3. It is being told to us. And the distance of the effort arm, I do not know, by 3, right? By distance in the load is 3. That will be your 60 by 3, because this is being told to us. This is 60 by 3, which is 20 centimeters. It is being lifted up. Then you're given 4 pulley systems here. 4 pulleys here. Draw a neat label diagram to use them so as to obtain a maximum mechanical advantage equal to 8 in your diagram. Okay, we want 8 mechanical advantage there. So how much is this here? 1, 2, 1, 2, 3, 4, 5, 6. 6 to the upward, and but all of them are not fixed, na? So that is now, we will not go with that way here. We will be just going up with my only this much. Yeah. So I will show you here for this part. How are we going to do this? Yeah. So as you have four pulleys here. So I would say the first part has got some N Newton load. And then it has been distributed into two things, which is N by 2 by the next pulley, right? And this N by 2 again is being split into two things by the next pulley, which is N by 4 ho gaya. Third pulley has done that. And then next pulley will be doing it as N by 4, half of that, half of that, half of that, just nothing but. So my mechanical advantage here is the total, which is the N newtons divided by N by 8, which is your 8, nothing but. So this is how we get the mechanical advantage 8 using 4 pulleys and your strings, 3 strings as you can see here. So around the first pulley, 1 string, around the second pulley, another, around the third pulley, another, and the fourth pulley here. And here, as you can see, T1, T2, T2, here T3, T3, and T3. We just have now done in the previous thing also the same way, right? So that is how we go with. Okay, so you can try these questions and then come back to me, bacha. Okay, in case you have any of the doubts coming up with any of these questions here, there are some fixed questions also here, theory part of questions. I want you to go through them as well. In case you have any doubt, we will have one live session also on this. Don't worry about that. Okay, fine then. So let us stop meeting here. Okay, bye-bye. See you.